Voyager 1 discovered a mysterious wall of fire made of superheated plasma. Where the sun's influence ends and interstellar space begins, the probe's measuring instruments suddenly went haywire. Complex interactions between solar wind and galactic forces heat the edge of the so-called heliosphere to temperatures of up to 50,000 degrees. The glowing hot wall means that we are drifting through the universe in a fireball. Voyager 1 has not only revealed a fiery boundary, it's venturing deeper and deeper into an unknown realm full of surprises that could change our view of the universe forever. In 1977, NASA sent two small ambassadors into space, Voyager 1 and 2. The goal of the two simple probes was to explore the outer planets, but their journey continued. Today, almost half a century later, Voyager 1 and 2 have discovered something that is revolutionizing our understanding of the edge of the solar system. A zone of superheated plasma that acts like an invisible wall of fire. This zone lies in the so-called helipause, the point where the solar wind stops and the interstellar medium begins. For a long time, it was thought that this transition was calm and clearly defined. But Voyager 1 and 2 showed something different. A narrow region with temperatures between 30,000 and 50,000 Kelvin. That's up to 50,000 degrees Celsius. In this extreme zone, there is no fire in the classical sense. Rather, the harsh conditions are caused by extremely high-energy particles whizzing around in an almost perfect vacuum. Plasma compressions caused by the collision of solar wind and interstellar particles, and above all magnetic reconnecton, release extreme energies here at the edge of our solar system. When the sun's magnetic field and the galaxy's field rub against each other, a kind of cosmic hissing sound is created that no one can hear but which Voyager 1 has measured. Scientists were thrilled. When even more unexpected things appeared at the end of the heliosphere, the sun's magnetic field did not appear to undergo any significant change beyond the firewall. They remained active even after the firewall and aligned as they are generated and emitted by our sun. This contradicts previous models and points to a deeper connection between our solar system and the galactic environment. The firewall is not an end. It is a transition, a place where incredible and previously unknown forces collide. The Voyager probe shows us that the boundary of the solar system is alive, and it speaks. Beyond the sun, the pulsating gateway to the galaxy. The moment Voyager 1 left the sun behind was in August 2012. The probe was the first man-made object to break through the invisible boundary where the sun's influence ends, and the interstellar medium begins. The expectations were clear. A smooth transition, a gradual decrease in solar activity followed by a new environment. But what the probe recorded was anything but calm. Instead of a gentle change, Voyager 1 encountered a narrow zone of extremely hot plasma, temperatures between 30,000 and 50,000 Kelvin or up to 50,000 degrees. The particle density was minimal, but the energy of the particles was enormous. What the probe discovered here was not a wall in the physical sense, not fire as we know it, but a high-energy phenomenon that surprised the researchers. 6 years later, Voyager 2 followed suit. In November 2018, its almost identical twin also flew through the wall of fire. Voyager 2's instruments are slightly more sensitive, and the second probe was able to provide even more detailed data from a wall of fire at the end of the solar system. It also measured similar temperatures and magnetic turbulence. This made it clear that the wall of fire was not a one-off event that Voyager 1 had perhaps measured by chance. It is a real permanent phenomenon at the edge of our solar system. What makes this discovery so groundbreaking? Firstly, the helipause did not turn out to be a static shield as previously assumed, but rather a dynamic transition zone. The extreme heat is generated when the solar wind encounters interstellar particles and through magnetic reconnection, a process in which the magnetic fields of the sun and the galaxy connect and release energy. Secondly, the orientation of the magnetic fields beyond the helipause was unexpected. It had been assumed that the galactic fields would be oriented completely differently from the solar fields. However, both Voyager probes show that the fields are surprisingly similar in orientation. This suggests a deeper connection between our solar system and the galactic environment, a kind of magnetic dialogue between stars and galaxies. Thirdly, the wall of fire is more than a physical phenomenon. It is a gateway to the galaxy. It marks the point at which we leave the direct control of the sun and enter the open interstellar medium. Everything beyond it is no longer part of our solar system, but part of the cosmic whole. For science, this means that models of the heliosphere need to be revised. Shielding against cosmic radiation, planning interstellar missions, assessing galactic influences on Earth. All of this now depends on a better understanding of this boundary zone. Voyager 1 and 2 did not just visit the outer planets. They crossed the threshold where our star ends and showed us that there is no empty nothingness waiting there, but a pulsating transition. The wall of fire is not the end. It is the beginning of a new story. The story of our connection with the galaxy. A dizzying dance through the galaxy. Our solar system orbits the center of the Milky Way at a speed of approximately 828,000 kilometers an hour. One orbit takes around 225 million years and is not exactly circular, but slightly elliptical, influenced by the gravity of other stars, interstellar gas clouds, and dark matter. During its journey, our solar system constantly passes through different regions of the interstellar medium where interactions also occur. This thinly distributed mixture of gas, dust, and magnetic fields, which exists as infinite space between the stars, has hardly been explored. Every bit of data from Voyager 1 or 2 is a special treat for researchers. The movement of our solar system has a direct impact on the shape and behavior of the heliosphere, the bubble of solar wind that surrounds our system. In denser areas of the ISM, the heliosphere is compressed, while in less dense regions it expands. This means that the boundary of our solar system, the helipause, is not a fixed point but changes dynamically and wafts through the universe a bit like a jellyfish. Voyager 1 has been flying directly through the interstellar medium since 2012. Although it's not far beyond the solar wind, it's not completely free of gravitational influences. The Sun continues to exert a weak gravitational pull, and the total mass of the Milky Way also influences the probe's trajectory. It's incredible, but the actual movement of the probe is still largely determined by the original momentum it received at launch. In 1977, Voyager 1 was launched into space at around 18,000 kilometers an hour aboard a Titan IIIe probe. Since there is no significant friction in space, its flight direction has remained stable ever since. The probe has therefore been following a predictable trajectory ever since. It continuously measures the properties of the ISM, such as particle density, magnetic fields, and radiation, providing unique data about the environment beyond our solar system. This information helps scientists better understand how our solar system interacts with the galactic environment, and there is still much to discover here. Overall, it has become apparent that the movement of our solar system through the galaxy are a far more complex process than previously assumed. After almost 50 years, Voyager 1 is documenting every day how external influences affect the structure and boundaries of our system. Time capsule in interstellar space. Will Voyager 1 and 2 ever encounter aliens? That's quite possible because these two can travel for millions of years until they eventually fall apart or are attracted by a distant star system. When the two probes set off in the late 1970s, we didn't know much about the outer planets. We had never seen accurate photos of Jupiter or Saturn and knew no details about Uranus or Neptune. At that time, two pioneers set off for completely unknown worlds, and no one knew what awaited the two probes there. It was clear that Voyager 1 and 2 would continue flying after their primary mission, but no one knew how long contact with them would be possible. In case these two ambassadors of humanity should ever fall into the hands of intelligent beings within or outside the solar system, both probes were equipped with a golden record. This gold-plated copper disc contains image and sound information about humanity, various types of music, readings in 55 languages, and illustrations of our life on Earth. Technically speaking, these two messages to humanity are not high-tech machines and cannot be compared in any way to 21st century probes. But they are ingenious and extremely durable in their own way. Developed in the 1970s, long before the digital age, they work with 8-track tape recorders, 1970s computers, and a power supply from radioactive decay heat. Despite, or perhaps because of their simple design, they are still transmitting data from a place so far away that we can hardly imagine the enormous distance. Over 20 billion kilometers away, it now takes a signal almost a day to travel through space and time to reach ground control in California. Many instruments are being gradually shut down over the years to save energy for the probe's important onward journey. In economy mode, central systems will remain active until at least 2026, sending us more exciting information every day from regions where no specific work has ever been done before. When will pioneer new horizons reach the ISM? Have you often wondered what actually happened to the other space probes that were launched into space 40 or 50 years ago? Probes such as the Pioneers are practically indestructible and will continue to fly forever unless they eventually burn up in a star or are crushed by a planet with an extreme magnetic field. Pioneer 10 and Pioneer 11 were also launched in the 1970s and left the solar system for the stars before the Voyager probes. Since both had less power capacity than the Voyager probes, contact with Pioneer 10 was lost in 2003. Pioneer 11 has been out of reach since 1995. Yet, both are still on trajectories that are expected to take them into the ISM around 2027, but we will no longer receive any measurement data from them. A more recent probe on an interstellar course is New Horizons, which was launched in 2006 and delivered the first real images of Pluto in 2015. The probe is currently in the Kuiper Belt and will reach the interstellar medium in the 2040s at the earliest. Although it's still flying within the heliosphere, New Horizons has already been tested for interstellar navigation. If the probe survives until it enters the ISM, it will be used to observe stellar parallaxes, and its primary mission will be to determine its position relative to the Milky Way, thus creating the first detailed map of our position in the galaxy, which could be an important step for future interstellar research missions. Between 2036 and 2041, NASA will launch the Interstellar Probe, the first probe whose sole purpose will be to explore the structure of interstellar space. After only 16 years of flight, the first interstellar probe is expected to penetrate deep into the unknown realm between the stars until it reaches a boundary beyond which no one today can say what lies beyond. Click subscribe now. The best videos are yet to come.